Okay. Well, welcome to section number 10, the last section. Mm, sad. Here's the QR code for today, and the question is very reflective since it's our last section. The question is essentially what's a happy and what's a crappy from the summer? What's something that has gone well that you've liked, or what's something that's been kind of a downer of the summer? Um, my happy is probably working with y'all, and my crappy is I'm so tired. I'm so tired. I can't wait to get back to Georgia and for my head to hit the pillow and then to sleep for 20 hours. That will be nice. So today's section, we are going to try to pick up the pieces from the Tuesday lecture where I know many of y'all were a bit distracted by the looming exam. There were also some students who just got up in the middle when Tim was lecturing, walked over to me, and started asking me about a practice exam. I was like, okay, sure. So we have probably a lot to regroup on and kind of recap on. And then the other big thing that I want to do in terms of goal for the section is I want you all to have seen like 5 challenge problems, 5 or 6. And so we're going to try to do a lot of challenge problem stuff today. The way I've structured section today is kind of around big ideas or big themes that were in the lecture yesterday. And so we're going to use that to help kind of orient us rather than just doing kind of individual reactions. But are there any kind of logistical questions before we jump into section proper? Yeah. I think it's pretty likely it won't be. Yeah. Same with radicals. I think it typically is 1 and then it's done. So that means that you will have 3, like anything syntheses on the final, which is hard, and then you won't have the radical mechanism, which is typically radical mechanisms can be tricky, but they typically have a process that you can follow and work through the answer really nicely. And now we can just kind of give you anything, which is a little scary. But I will say the final exam has more mechanism on it than any of the other exams. And part of it's just we have more questions. Like we have enough questions to do that. But look at the practice exams for kind of the form and structure, and it'll be very similar. Cool. So, without further ado, are y'all tired of the transitions? No? Okay. Then I'll start us off with a transition. Let's do.
I knew it.
Let's talk about enolates. So our first big idea of this section is hydrogens on an alpha carbon to a carbonyl are acidic. So all the way back from lecture 2, you saw that alkanes had a pK of about 50. But here, the alpha hydrogens here to a carbonyl have a pK of about 20. So that's like orders of magnitude more acidic. And so there's something going on here that's going to make these more acidic than just a simple alkane. So if we deprotonate it, we form this structure that we call an enolate with a minus charge here. And this is a structure where that negative charge is stabilized by resonance. So that's making this a more stable conjugate base. So relatively, this is a stronger conjugate acid because more stable is like a weak conjugate base. There is an MO requirement. Just kind of like for an E2 reaction, our MO requirement was an anti-periplanar beta hydrogen and the leaving group. Here, the overlap that we need to happen is we need the sigma CH for the hydrogen that we deprotonate. It needs to line up with our pi star CO. And this is a thing that we are not going to ask you like on an exam really about this. This is something that's going to show up a lot more in Chem 27 in biochemistry. You're going to have a lot more of these MO requirements. And then there's also a challenge problem that we're going to do together today in section that talks about this. So this MO requirements, the kind of big part. So when a base would come along and deprotonate it, we just want these electrons to be lined up so they can go right into the antibond and then break the pi bond as it creates this alkene. The second big idea that's kind of connected to this is enolates, this structure that we just made, they are nucleophilic at the alpha carbon. So we can push down, kind of lone pair push like, and then push off this double bond to go and attack an electrophile. When we do that, we create an alpha-beta bond away from our carbonyl. And there are lots of different types of electrophiles that our enolate can attack, and that's kind of what we're going to talk about later today. So we have some kind of distinctions here of an enol versus an enolate. So an enol is just very simply an alkene and alcohol that are connected via resonance, enol. And then the negatively charged version of it is enolate. It's kind of like the difference between alcohols and alkoxides. So between these two structures, which do you think is going to be the better nucleophile? The one with a negative charge or the one that's neutral? A negative charge. The negative charge is going to build up electrons in a molecule, and so it's going to make it more likely to go and do an attack because you have this kind of concentration of electrons. So this is the better nucleophile. Which do you think would be more stable in acid? Do we typically have negative charge in acid? No. So enols typically happen in acid, and then enolates typically happen in base. So these are just some kind of differences between these and pointing out some trends with them. We also have this idea of the keto-enol tautomerization. So has anyone ever heard the word tautomer before in like another class? Tautomer or tautology? So essentially it means like a logical equivalence. So when we say keto-enol tautomerization, we're saying that these two are kind of equivalent-like things. And if we look at them, they're constitutional isomers. They have the same formula of RC2H3O. And so all that we are doing is changing where we put a hydrogen, so this hydrogen moves, and we're changing where we put our double bond. With this, we can think about these as two different kind of forms of the same molecule. I'm thinking about like two different forms of the same Pokemon or something. And we can interconvert between these with acid or base catalysts. So I'm not going to go through the full mechanism of these, but the main difference here is just in our protonation steps. Like in base, we would directly deprotonate, and then we would do a protonation to make it neutral. But in acid, we would have to protonate our carbonyl to make this a better acid, and then we would do our deprotonation. So it's just kind of doing it in acid or base. The main thing that we're changing is our protonation states and our order of our steps. So we have these two kind of different versions here. And the other big kind of powerful thing about this is, do ketones typically act as nucleophiles or electrophiles? Electrophiles, and we saw those reactions a lot in like lecture 3, lecture 5. But enols, we just said, are nucleophiles, and specifically nucleophiles at the alpha carbon. And so this is the kind of interesting thing where this process lets us switch back and forth between nucleophile and electrophile, which is kind of powerful. So, with that in mind, we have a bunch of different types of enolates that we can make, and I've kind of summarized it here. And this gives off the energy of like the choose your fighter of the different enolates here. So, sound cue, it was a little louder than anticipated. But here, our kind of basic ones are like aldehyde and ketone enolates over here. We can also do an enolate and ester. And we can even do one with a cyanide, and this one looks weird. This one looks weird as all get out. You might see it on the problem set. But it would react the same way of it push down, makes a bond, and then the CC double bond attacks. Push down, CC double bond attacks. Now if you have an alpha hydrogen that is between two carbonyls, it is even more acidic. And if one of those is like a ketone or aldehyde, it's even more acidic than that. So, generally speaking, a trend that you should know is dicarbonyls have more acidic hydrogens than single carbonyls. And you should know that ketones and aldehydes are more acidic than esters. Those are kind of the big trends. The other girl that I want to give a call out here is enamine. Enamine is a very similar structure to like an enol. It's the nitrogen version of an enol. So just like how an enol could push down and attack something, an enamine can push down and attack something. And we might see this shortly on a problem. I don't know. Also, I think I forgot to say it over here. Some books do enolates like this. This is not our preferred way of doing it for this class. These are resonance structures, but why is the one that we've drawn down here better? Exactly. The negative charge on the more electronegative element. And so this is the way we would prefer you to write it rather than the other one. So, but if you're looking at like outside videos or things, or even I think the Occam as a second language sometimes does it as the C minus. But okay, let's check this out. So, what functional group is this? Enamine, great. So the enamine. And we just said that this is kind of like an enolate. So it is going to be a good nucleophile. And then that would mean our other molecule is probably the electrophile. And what are some acceptor MOs on this electrophile? So we have the pi star CO. Anything else? Good, sigma star CBr. So which of these, just energy level wise, which of these is the better acceptor? What's our order of energy? We have sigma, pi, non-bonding, pi star, sigma star. So which ones are better acceptor or LUMO, lower energy acceptor? Pi star is. But if we look at this, does it look like we've reacted with that pi star? No, because we still have the pi bond. If we had attacked that pi star, we would have broken the pi bond. So that means that for some reason, this reaction is going to favor interacting with this sigma star. Do we see that carbon-bromine bond broken in the product? That can further kind of enforce our intuition there. So we're going to push down. This is going to do an SN2-like attack. We get to this structure where we've made a bond between this blue one on the original, or on the sigma star, and this green one on the enamine. And then there's one more carbon and a hydrogen. And we've created a double bond to nitrogen on it. Okay. So now we have this iminium structure. And it looks like everything's in the right place, but here we have carbonyl. And our reagent is H3O+. So iminium and H3O+, is that a reaction from exam 2 content that y'all learned? Yeah, exactly. So this is going to be your imine hydrolysis. And I'll let you write that out on your own when you're doing the problem set, because that's just kind of recreating the arrows. And that's from lecture 5. Cool. So again, a lot of this chemistry can intersect in interesting ways with reactions that you've already learned earlier in the class, and you'll see that kind of come up several times today. So let's also, so that was challenge problem 4b. Let's look at challenge problem 1 down here. And it's really asking us to explain, hey, we have two ketones, and one of them has a pK of around 40, one has a pK of around 20. Why? So, which pK is closer to what we would expect of an alpha hydrogen? Yeah, the left one. So we would expect this to do like an alpha deprotonation. And then this one is like, kind of like an alkane. So let's maybe draw our enolates and see if we notice anything. So first step is we need to find all of our alpha carbons. So can you take like 10 seconds and on each molecule try to star or highlight the alpha carbons to the carbonyl. We have all these, and we have alpha hydrogen, alpha hydrogen, alpha hydrogen, alpha hydrogen, alpha hydrogen. So, let's try drawing enolates in each of these positions. So, I'll maybe start with the left molecule. Here we have the enolate on the left. And I realize that like these kind of bridge structures we haven't really taught you how to draw. We would never like really grade you on your drawing of it, but to show you how I draw it, I'll do it a little bit slower this time. So you start off with drawing kind of a slanted line. Then on that, as if you were doing like a parallelogram, you draw two parallel lines going up. Then you draw two parallel lines going down. And lastly, you connect it. And then you add the little top hat. And the top hat typically has to kind of bend a certain way. It's typically not just like straight up because that like looks harder. But actually that didn't look terrible. So we have this enolate. And on the other molecule, the enolate that we could form is this. So, do any of these enolates make alarm bells go off? Specifically in relationship to some stuff that we learned in lecture 4. Did the alarm bell go off? Hmm. But stabilizing to me isn't alarm bells. What's an alarm bell thing? We're like, illegal.
Oh, the cowboy Texas carbon? No.
No, not Texas Carbon.
Maybe the
Yeah. So it's the idea that when we have a bridged ring, these atoms right here are called bridgehead atoms. And we had this rule from lecture 4 called Brett's rule. And Brett's rule says that you cannot place a double bond on a bridgehead atom. So this one over here would violate Brett's rule. And then also over here. So why can't we have a double bond on a bridgehead atom? Well, our double bond wants what bond angle? It's sp2 hybridized, so it wants a 120 degree bond angle. Yeah. So if it is wanting 120 degrees and it has to be contorted in a very specific way to do this like bridge structure, that is just going to be impossible, like geometrically. But I would encourage you to try to build that in your model kit. See what happens. So essentially what that's going to do is it's going to rule out both of these structures. And so we only have really one valid enolate that's going to form. And that's going to be this enolate with one of these hydrogens. Now I think the question also asks you to explain it in terms of molecular orbitals. So here we have the sigma CH, that's this kind of down axial one, can line up and donate into the pi star CO. So we get some good donation there, where these are going to overlap fairly well. This is not a chair, so it's kind of hard to see what that looks like, but if you will take my word, it does overlap and they are parallel. Over here, you have your pi star that's like up here. But then your sigma star, these are kind of going down in a way. And so there's just no overlap that's really possible. So that's kind of an ammo way of explaining it. Later on that question, you're presented with these two molecules. And you were asked to kind of, one, draw like the mechanism, and then explain why this happens. So, like, what's the difference between the star material and the product here? We have like a deuterium here. And initially we had a hydrogen there. So we need to remove the hydrogen and replace it with a deuterium. What kind of hydrogen is that? It's an alpha hydrogen, right? So we can take our OD minus, which is like OH minus hydroxide but with deuterium, have it deprotonate, push in, form an enolate. And we would kick off HOD, HOD. And then we need to grab a deuterium from somewhere. Where are we going to grab a deuterium from? D2O. DOD. And that is heavy water. So that would be our mechanism. And then maybe the kind of question that's more interesting here is why did that one happen versus this other beta hydrogen? Or alpha hydrogen, I should say. Like, why did the blue one happen and not the green one? The MO stuff here. So, our antibonding orbital is like this, and this has better overlap with it than the one that's going kind of down in a way. Cool. So this question really was just trying to explore the MOs of this. But, yeah, we are not really going to ask you about the MOs in other contexts. Yeah, Lexi. Because sp2 hybridized, and so it's not a real chair. Yeah, it would actually be more kind of like planar-ish, because it's trigonal planar. But, yeah. Cool. Any questions on these kind of basics of enolates before we jump into our first big family? Yeah. Oh, enolates here, so esters are less acidic than ketones aldehydes, and dicarbonyls are more acidic than single carbonyls. Yeah.
Not what it seems.
Does anyone know what that's from? Yes. Do you all know that there's a reboot of it that's coming? One of my friends I went to Harvard with, she's a writer on it. Yeah, I was like, oh, okay, pop off. Mm. Sorry? No, like it has the original, and then now they're the parents and they have kids.
But JT also
No, I don't think. But the older brother is back. Selena Gomez might be. Not sure.
But Harper will also look better.
It's been a minute. Okay, so our next big reaction family here, and our big theme for this, is enolates. We know our nucleophiles now. They can attack ketones and aldehydes. And when we do, that is the aldol reaction. So, here we would have some sort of enolate and some sort of ketone or aldehyde. And we could do as a first step forming an enolate. So it might just look like two carbonyl things to start. So it might just look like this. But the enolate can push down, attack a carbonyl. When it does, we get to this intermediate structure where we have made an alpha-beta bond. Again, that alpha and beta bond being created by enolates attacking is important. And then what we are going to do at this point is we will neutralize it with water here. The product that we form here, we call our aldol addition product, where we've added the two things together. And functional group-wise, its government name is a beta hydroxy carbonyl. So we go to the beta position compared to a carbonyl, alpha beta, and then we have an OH on it. This, again, is the government name, beta hydroxy carbonyl. Its nickname is aldol, A-L-D-O-L. And that, you have to remember, is only for beta hydroxys. If it was an alpha hydroxy, that's not an aldol. If it was a gamma hydroxy, that's not an aldol. So, beta hydroxy aldol. And do you remember in the imine mechanism how we got to that neutral intermediate of the hemiaminal and we like paused for a minute? So this can be like that. It can be a little pause, or it can fully be the end of the mechanism. We could stop here. So you can get this as a product coming out of the reaction, or you can drive the reaction even further forward, typically with heat. Heat is a way to kind of control it and to get it to react more. And you can get a different product. So if this goes on to react, what we could do is we still have an alpha hydrogen that's pretty acidic and we're in base. And so we would deprotonate at the alpha position. And then we have this kind of weird step. So the weird step is we lone pair push down from our enolate, move over the carbon-carbon double bond, and then kick off the OH. So this step, I kind of liken it to, like, imagine you're playing in the pool and you like have like a water and you want to get like a big wave up and push your friend all the way out of the pool or like off the edge of the river or waterfall or something. Ooh, I like the waterfall metaphor. You're kind of like get in the water and goodbye. So this is kind of like a lone pair push, right? Like it has this lone pair push arrow, but it's even stronger than that, being able to kind of push off things that aren't necessarily great leaving groups. Like this OH, we know alcohols are not great leaving groups. And so if we were just doing a simple lone pair push, that's not something that we would kick off as readily. But this kind of fancy lone pair push can kick off an OH minus in base. If we were an acid, we would want to protonate this first and make it OH2 plus to kick it off. But this step, it has a special name. It's called an E1CB mechanism. So the E comes from the fact that it's an elimination. We've made an alkene and we've kicked off a thing. So elimination. And the CB comes from the fact that this is the conjugate base of our aldol product. It is, we've deprotonated it, this is the conjugate base. So a very common mistake, and I'm going to show you the mistake, and I guarantee 15 people or more will make it on the final exam. Very common mistake is they deprotonate here, kick off the OH. That, arrows-wise, you could just draw the product after that, but that is just not what happens, because it ignores the fact that there would be this kind of resonance here, and the electrons are always going to go towards the more electronegative atom. So, don't fall into the trap. I have my old exam from OChem 2. This is typically the unit that's taught towards the end of OChem 2. And on my exam, I missed this. And the grader did like -5 E1CB. I said -5, and they said -5. I said, for us, I don't know that it would be -5. It would probably be like -3. Because, like, I mean, we grade based on arrows, and we grade based on structures, and it skips a whole structure and does the wrong arrows. So, be better than me. Learn from my mistakes. The E1CB mechanism. You'd never be asked to name this, but I think it's helpful to give it a name so that it's something that you remember rather than the trap that you fall into, you know? So, this product that we get, we call our condensation product, our aldol condensation product. And we call it a condensation product because we've kicked off an OH. And we've kicked off kind of like a water, so it's condensing. This, structurally, is a functional group that you know. What functional group is this? Maybe. Enone, lecture 3. So this lecture has a lot of throwbacks, again, to earlier lectures. And so here we now know how to make an enone. And in lecture 3, we did a lot of reactions starting with an enone. So a great way to do something as synthesis. The other thing is, it's like government name, is an alpha beta unsaturated ketone, or unsaturated carbonyl. So you might remember from bio, like saturated versus unsaturated fats. Unsaturated has a double bond. So this says, hey, we have a double bond between alpha and beta, and it's alpha and beta to a carbonyl. Or you can just call it enone. Cool. So this is the aldol reaction. It's one of our major reactions. I would be so surprised if you did not see it on the final exam in some form. let's do a practice with some of it. So this is challenge problem 7. With this, our product doesn't look like an obvious aldol, right? Like there's no OH, there's no double bond. But we have this like dicarbonyl here. And what do we know about the alpha hydrogens of dicarbonyls? They're pretty darn acidic. So this could be a really good like enolate nucleophile. And then over here, we have an aldehyde. And this R group over here is like this big scary looking thing that just is irrelevant. And so I'm just calling this R. And this, does it have any alpha hydrogens on it? Are there alpha hydrogens here? No, that carbon has 4 bonds already. Is this an alpha hydrogen? It looks like it is. But here, is it on an alpha carbon? No, it's attached to the carbonyl. In order to be on an alpha hydrogen, it has to be on a separate carbon from the carbonyl carbon. It has to be a neighboring carbon. So that's a trick that often trips up students initially. Then there could be one there. Because this is what the R group is.
Oh, sorry.
Oh, yeah. So, cool. Let's start this. And we don't know exactly how we're going to get there. But let's start and make our nucleophile our enolate. So we would do OET minus. Here, push in, push up. And does it matter if I went and formed the top enolate or the bottom enolate here? Are these two different from each other? No, and it's symmetric here. So it does not matter which one that we form. And then we now have our nucleophile that can go and attack our electrophile. So I want you to take approximately like a minute and a half and try to recapitulate the arrows here from our nucleophile enolate attacking a carbonyl electrophile. And I want you to get to the aldol condensation product. To help you out, what I'm going to do is I'm going to draw the aldol addition product. And the aldol addition product looks like this. And I'm going to draw the aldol condensation product. And so it's going to be kind of filling in the steps to get there. So it can happen in acid, but we are doing it in base. So I'll put up these mechanism steps for you as you try to recapitulate the arrows. And then here are the structures of the aldol addition and condensation product. I did just get an email from Tim, and he's willing to make one of the practice exam video solutions. So if he can do one and I can do one, then we can probably get it done. So we'll try to make those again. Yeah. Because you can draw the arrows and go right to the product, seemingly. So maybe let's get into it a little bit. And can I get a volunteer to tell me some of the arrow pushing that they did to try to get to the Aldol Edition product from these two? And do not feel like you have to get everything right. It's actually helpful if you're a volunteer and you make a mistake because other people probably made that mistake. So, do I have a volunteer? Yes. Excellent.
Okay, so actually,
Mhm.
before we having the ability to make the diagram,
Mhm.
like push the right hand and then the extreme down, and then have the right arm just really attack and come down, and then push the left the other back to the left and the extreme.
Beautiful. And so, when we do that, I'm going to move this over very slightly. We are making a bond between this green carbon and this blue carbon. So, when I try to draw this, I know I've reformed my carbonyls over here. We've made this blue-green bond, this alpha-beta bond. And then the blue one, I should have an O minus, an H, and an R. So what do we need to do to get to our aldol addition product, Lexi?
What do you say? What do you get the minus right into the right?
Perfect. If you want to use the SOL abbreviation, you can, but this is great. So we got to the aldol addition product, our stable kind of neutral intermediate. Can I get a different volunteer to help take me from the aldol addition to the condensation product? So many volunteers, I don't know who I'll pick. My gosh. Yes, please.
So I took each from
Great.
and I could put it to
Perfect.
that way, and then go
Great. Now, does it matter whether we went up or down? Or, sorry, we can't go this way. But could we have done this? Yeah, they're the same. They're equivalent carbonyls here. Good. So, oh. Now, Vanessa, I might ask you a hard question. So, you did the correct steps. What would have been the incorrect thing to do here that's the easy trap? Exactly. And again, this is what we want to avoid. Because this, we always are going to honor this resonance that exists here and make this more stable negative charge. So when we're here, how do we get to the aldol condensation product? Excellent. And this is our E1CB step. Great. So we now have this kind of enone thing. And it looks similar to our product, but our product is an alkane. Okay? Well, let's look at step 2, what this reagent is. What does this remind you of? Okay, what other reagent does this remind you of? Yeah, it looks kind of like an NaBH4, where we've traded a hydrogen for a cyanide. So, this is a variant of NaBH4 that only adds 1,4 to an enone. So another kind of full circle moment connecting back to lecture 3. Lecture 3, if we wanted to add a hydrogen only 1,2 to an enone, we sprinkled in CeCl3 to our NaBH4. And now we learned that there is a variant to only add 1,4 to an enone as well. And this is something where it says in the problem, I was just wanting to kind of like talk through it a little bit. So the way we'd write it out is like BH3CN and draw out one of those boron hydrogen bonds explicitly. We got a negative charge on boron, just like BH4 minus. And then we would do a conjugate addition. We would add 1, 4 and push up to a carbonyl. Analyte chemistry is quite pretty. Like it is like beautiful mechanisms. You can accomplish a lot of different things with it. It's the chemistry of nature. Like nature as an organic chemist does, like chemistry. So now from this to the product, what do we need to do? And yeah, we need to grab a hydrogen from the solvent, and our solvent for this is HOET. Great. And so this, you might not remember from the time, but I called this an alpha protonation. And hey, now that we have lecture 10 stuff and we're doing all this alpha carbon chemistry, that makes sense. We're protonating something at this alpha position relative to the carbonyl. And we can also see that here in the product, this has a hydrogen, whereas this did not. So that could also help us. Cool. So that's our aldol mechanism of challenge problem 7. Challenge problem 2a, just to touch on briefly, again, going back to some of this like lecture 3 stuff, what reagent is this? The Grignard, everyone's favorite. And just some notes from things I saw in the box problems and synthesis. Grignards can only have carbons and hydrogens. So you could not have like an OET MGBr. You could not have like an SET MGBr. It has to be only carbon things. You can't have an oxygen or sulfur in it. But Grignard, you would imagine, lecture 3 style, you would do this, right? Does it look like we have done that in the product? No. What functional group did we make? An enone. So we know that we've done some sort of aldol if we made an enone. And then, where did our phenyl group go? She's free. She's a benzene now. So, this thing was not acting as our nucleophile. What do we know about Grignards other than them acting as a nucleophile? They're bases. And that's the thing that we tried to kind of keep coming back several times now. It is acting as a base. And so, our Grignard reagent, all it's going to do in this case is deprotonate the alpha position and form an enolate. When we do that, we're going to get pH with an H on it. This is benzene. Because remember, the pH phenyl ring is just benzene as a substituent, but now it has a bond to H where the MGBr was. So, we've made an enolate. And then, if we were trying to map sodium to ozone on the product, we have this R and then this 2-carbon unit. Well, we have that here, but we also have that here. So what does this enolate attack? If we have 2 of these 3-carbon units in the product, then what does this nucleophile attack? Another equivalent. Great. So, you're going to push up and attack. And then from here, I think that you can do the aldol condensation. Or actually, no, I'm going to stop and show one more thing. So the intermediate that we would get looks like this. And then what would the next step be here to get to our aldol addition product? Step that got here, what would we do? It would protonate, right? But my question here now is, what do we have in our mixture that could protonate this? So, benzene here, these aren't very acidic hydrogens. Like, yes, you're right that it's technically the conjugate acid here, but like this O minus is not a strong enough base to deprotonate a benzene. That would be almost like deprotonating like a alkane. Not quite as hard, but still, we don't have a good acid here. So what we have to do in this case is we have to protonate it with the H plus workup in the second step. And then, this is going to be the tricky part that you're going to have to kind of figure out when you're doing the problem set, is then you are going to do the aldol condensation in acid, because we are in the acid workup. So your protonation states are going to be a little bit different. For the section handout, I focused on the mechanism in base just because it takes up a lot of space here. The mechanism in acid is in the lecture notes, so you will see that. But from here on, we start the acid workup, so everything else has to be in acid. So I'll let you kind of work through the nitty-gritty details of that as you're working through it, so you might want to look at lecture notes. Cool. Okay, we have like a mini transition, so I'm going to do like a mini transition to the other big idea in this section. So, the next kind of big idea related to this is we have lots of different kind of variants of the aldol reactions, depending on the specific identity of the ketone or aldehyde that we are attacking with and that we are attacking. So, for example, if we have something just like this one that we just did, where a molecule is attacking another equivalent of itself, so one of them becomes the analate, one of them becomes the electrophile, this is what we call the classic aldol. This was the original reaction that was discovered. But if we have an analate attacking a different molecule, then we call it a crossed aldol. If they're on the same molecule, it's an intramolecular aldol. And then this reaction is fully reversible. So we call the reverse the retroaldol, and it's literally the exact same mechanism in reverse, beat by beat, undoing arrow by arrow. So this is one I'm not going to go through beat by beat because it's literally the reverse step. But with all these different flavors of it, I was trying to figure out a way to kind of organize it mentally. And this is something that I was so surprised that many of the like major organic chemistry textbooks don't talk about this. But I understand these best with their Cha-Cha slide concordance. So each of these types of aldol reactions corresponds well to part of the Cha-Cha slide, which is that something that's in your kind of cultural mind? Like, do you all know the Cha-Cha slide or know of it? Kind of. Well, we have some audio clips to jog your memory. So the classic aldol corresponds to
slide to the left, slide to the right.
Because literally it's like slide to the left, slide to the right, they're the same molecule, so just sliding. Then, what do you think the crossed aldol corresponds to?
Crisscross, crisscross.
Exactly. And then the intramolecular aldol, it's kind of like this molecule's like wiggling around, and then it interacts with itself, and so it is.
Cha-cha, real smooth.
It's doing a little wiggly dance and coming together. It's also all giving kind of the energy of.
Last time it gets funky.
Because, like, I mean, it's a little weird doing intramolecular reaction. And then the retroaldol is, of course,
Reverse. Reverse.
and it also has kind of take it back now, y'all energy. And since we're here, we have to do the, like, obligatory.
Freeze. Everybody clap your hands. Come on, y'all. Check it out, y'all. Here you go.
So it's a thing that I don't know why I haven't seen it in any of the major textbooks yet, because it's so obvious. You know, it's really just there. But yeah, I remember like thinking 2 years ago, like, how could I organize this? And I was like, duh, the Cha-Cha slide. So, again, this is a thing where we are not going to ask you to label the different versions, but I think it is helpful to mentally compartmentalize the ways in which you can see this reaction in different contexts. And a lot of this only really depends on the exact identity of these molecules that are being attacked. But they're all like ketones and aldehydes being attacked by enolates. An essential skill connected with aldol chemistry, really all of lecture 10 chemistry, is being able to do disconnections. So one, how do we like touch the earth and be like something happened here, an aldol reaction happened here? And we have to look for two functional groups. One, we are looking for an enone here, an alpha beta unsaturated carbonyl. Or two, we're looking for an aldol, where we have a OH beta to a carbonyl. So what I want you to do in all of these is I want you to find the alpha and beta position where you think an aldol reaction has happened, and then I want you to draw a cut between it, and then we will try to go together and see what the molecules were before the aldol happened. So I'll give you like a minute. Now it's time to get funky. Reverse. So how'd y'all do? The first two are a little bit easier, the third one's harder. So here we have an enone, right? So we can count alpha beta away from it, and we know that aldol likes to make alpha beta bonds, we cut. Here, carbonyl, alpha beta, beta hydroxy, so we have an aldol. Where is our aldol or enone here? Well, is this an aldol? No. It's an alpha hydroxy. And then, is this an enone? No, because that's an sp3 hybridized carbon. So what is this? It's a trick question. Thank you. Thank you for coming. Thank you for playing. Stay vigilant. You must stay vigilant. It's so hard to spot these things because they look so similar. And so being on the lookout for these specific functional groups is going to make it so easier for you to see what reaction happened. Okay, so if we cut over here, essentially we need to know which side was our enolate and which side was just our electrophile that we attacked. And to do that, to figure out which is which, we have to look to the mechanism. Well, this carbonyl carbon, did it come from our nucleophile or our electrophile? This carbonyl. The nucleophile. It was this enolate, right? And that carbonyl is there to the end. So we know whichever side has our carbonyl was our enolate nucleophile. And the other side was our electrophile. So when we split this up, we know which side, the left side or the right side, was our nucleophile, the enolate. Left, because it has the carbonyl. So here, you had an O minus enolate, and you had a carbonyl. And then if we wanted to take that enolate back one step further, we could have made it from this ketone. And we see, this is a classic aldol, where a molecule attacked another equivalent of itself. Okay. And then, if we cut here, which side, the left or right, is going to be our nucleophile enolate? The right. So it's because we have our carbonyl over there. So enolate there, where the carbonyl was. And then where our OH is, that's our carbonyl that was attacked. And has a little hydrogen on it because it was an aldehyde. Cool. And we could, again, go back one step further. And we could have said, we had this to start with before we made our enolate. So this disconnection skill is going to be helpful, especially when you're doing your investigative journalism and you are like touching the earth and said, who cooked here? What happened? And we're about to have to do that journalism. So I bring to you Exhibit 3A, Challenge Problem 3A. Ugh. Ugh. We know it's in Lecture 10 stuff because it's on the problem set. Do we see any of our functional groups? What functional groups do we see? We have an enone, which we know can be made from an aldol. Okay. What do we have in the starting material? We have a ketone, but do we have any of our like Lecture 10 functional groups? What's the other one to look for other than an enone? Aldol? Or like yes, enol is one. But this, alpha, beta hydroxy, this is an aldol. And it looks kind of weird. It's hard to spot at first. And that's why there has to be some like explicit practice done to spot it. So we're going from an aldol to an enone, which we know happens in our aldol reaction, right? But if we were to just take this aldol and make it into its enone, that would make the double bond here. And like that is not the product that we have. We have done something much weirder. So this is where it's kind of tricky and disconnections are helpful. So what I want you to try to do is I want you to try to do a disconnection of this, which would be equivalent to doing like a retroaldol, where you undo this aldol, cut between the alpha beta bond, and write out the enolate nucleophile and carbonyl electrophile. And I also want you to do the same thing over here with the other side, where you cut the alpha beta bond, make one side a nucleophile, enolate, and the other one the electrophile carbonyl. So we know the carbonyl side on both of these was the enolate. So we disconnected that alpha beta bond. And here we have it. Now, how do these enolates look different from each other? Like, what's different about these two molecules? Yeah, one has this kind of more internal enolate, and one has the more terminal enolate. So, why don't we just undo our enolate? Let's do our little tautomerization, grab a hydrogen, and then we get to this little straight chain. So we have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. So we know that deprotonating here in the inside position, and this is symmetric so we could do either, that would make this inside enolate. And then if we deprotonate on one of the outside ones, we would get the outside enolate. And so if we want to get this outside enolate, we could just deprotonate at one of these outside positions. And then we would be here. From there, once we have the right enolate, we just do our aldol condensation. So I love these problems. I think that they are so cool because you're having to kind of think backwards, get into this like long chain form a different enolate on the same molecule, and then do an attack, a different alcohol attack. So I was trying to think what it was. I didn't have the sound cue prepared for it because I didn't know what it was. But I remember there was a dance where it's like you go down and then you go like up. Da-da. I don't know. Like you kind of crouch down and then like pop up. And then I said that to the 8 a.m. section and they were like, oh my gosh, of course. Rasputin? Rasputin dance? And then I Googled it in the 10, but it's gonna, apparently this is from Dance Dance, Just Dance, maybe? But, where is it? And apparently there's a dance where you're kind of popping up and down. But that's why I think of this. Like it's in one ring, it's down, then it kind of pops up, and it's straight chain, and then says, now I'm going to change my position, and I'm going to pop back down in a different way. So, love these. I think they're a great problem. Questions on aldol. I know that this was a big section. Okay. And now the time has come for us to talk about the Claisen reaction. So this one I'm going to do a much lighter touch on because it really parallels a lot of the aldol reaction. But our big idea here is enolates can attack esters too. And this is what is called the Claisen reaction. So the whole other one, we were attacking ketones, aldehydes, that's aldol reaction. The big difference here, when we attack an ester versus a ketone or aldehyde, here this is the attacking step, the difference is here. So when we have attacked an ester, the ester has this OR group on it. And here, now when we have the O minus, we have a leaving group present. And so we can push down and kick off this OR, and we make a beta dicarbonyl. We have two carbonyls that are alpha beta to each other. And that's going to be our final product over here, a beta dicarbonyl. There are different flavors of it. You could do a beta diketone, a beta keto ester. Like there are lots of specific names, but we have two carbonyls beta to each other. But when we reach this step in the mechanism, we're not done yet, folks. We have just created a dicarbonyl. And so what do we know about the hydrogens between two carbonyls? They're even more acidic than one carbonyl. So if we are in basic enough conditions to deprotonate this hydrogen, we are certainly going to be in basic enough conditions to deprotonate over here, and it fully will happen. Like you will do this deprotonation. And so we have to deprotonate it, push up to the O. And then we go into step 2, which is an H plus workup. And the H plus workup, we go and grab that hydrogen back, which is really annoying. Like this whole thing, it's like we formed our product that we want, and then yet we have to deprotonate it and then reprotonate it. And it's just like, just let me rest. Just let me live. But this is another thing where like, if you just stopped here and didn't do this, minus 3 points. Yeah.
Is it like the ester group? Is it the same? Like it's like the same, like ester and base kind of like ester group?
Yeah, like how you would have to form the carboxylate and then do an acid workup. Yeah, exactly. So it's the idea that we're still in base and we have an acidic hydrogen, and that is just going to be deprotonated, and we need to kind of reflect what's happening. It's really, really annoying. But let's try to work out some of the details of this just by doing a mechanism practice. So I'm going to do this with y'all and we'll talk through it. We have our good friend Naomi, and typically for Claisens, we want to use the alkoxide that corresponds to the ester. So like, for example, if this was OET, we would do NaOH, ethoxide, I don't know. We don't have a cute name for her. So here, we have a base, and then we have this molecule. What do you notice about this molecule? The overall structure. does it matter whether we deprotonate here or here? Why does it not matter? It's the same. There's symmetry in this molecule. So we know that we're going to deprotonate one of them. Let's just do one side. It doesn't matter. We can deprotonate. Oh my gosh, so many carbons. We have our enolate, we have our ester. And we're forming a ring, so we know we've done something intramolecular. So let's have our enolate push down and attack the carbonyl of the ester. So if we do that, this is where we use our superpower, which is numbering. We know our carbon, alpha carbon here is the one that's going to be the nucleophile. 1, 2, 3, 4, 5. So we form a 5-membered ring. And I'll number it 1, 2, 3, 4, 5. I think I'm going to make this go down a little bit. On 5, we now have an O minus and an OMe. And on 1, we have a little dangly ester. Okay. So now this is the step where we form this tetrahedral intermediate. We have the O minus. We can just push down and kick off the OMe. And then we're done. See, you're making a face, Vanessa. You're so right. This was the trap. This is -3 points on the exam. Stay vigilant. Stay vigilant. It's so easy to do. It's so easy to do because you're like, well, we've drawn the product. We're done. We're done. But remember, we have formed a dicarbonyl, and we are in base. So that hydrogen, yes, indeed, it's super acidic. So our OMe must deprotonate it. We're not done yet, folks. And then, in an exciting turn of events, we just undo it. And we have this go and grab an H+. So, do not just go directly to the product.
Can you push up from the left side? That's
Oh, you mean like, why did we go this way versus this way? So that's a great question. If you have the choice between pushing onto an ester carbonyl or a ketone or aldehyde carbonyl, you will always push up on the ketone aldehyde. And it's because the ester here has its own resonance going on. So it has this resonance coming from that side. So if you were to push up here onto the carbonyl, that would be competing with this resonance, essentially. Whereas the other one doesn't really have any resonance going on, and so it's easier to just push up on the ketone aldehyde. Great question. Yeah. Now, this one, child problem 3b, we're not going to fully do, but it looks like a methyl has kind of magically migrated over to the other side. So this is going to be one where we're doing our Rasputin dance, where we have a beta dicarbonyl in both of them. Beta dicarbonyl. And this, if we had done a second step H+, that would go and make this back into a carbonyl. And what we are going to be doing is, or what you're going to be doing on the problem set, is a retroclason. So you're going to undo the clason that made this. You're going to get to a straight chain molecule where you will switch the enolate and then do a clason reaction, clason condensation. So that's going to be kind of the reaction scheme to follow for this. Very similar in vein to the aldol one that we did at the bottom of the other page. Again, I don't want to spend a ton of time touching on it because the next big idea is just you have all the different flavors of the Clasons. You have the classic Clason, cross Clason, intermolecular, and retro. I provided the retro Clason mechanism here. And then there's also some disconnection practice that I think would be really good and helpful to do. In the annotated version, I'll have that done on there, so you'll be able to see it and practice it yourself. But I think that that's all I really want to say on the Clason for now. Do y'all have any questions related to this? I have a question. Is that from the Fire Festival? Is that
Oh no, it's
FYI.
from the orientation. I get that a lot.
first
though.
year
First year retreat experience,
work?
right?
Yeah.
But I know what the Fire Festival is.
Yeah. Well, I don't quite know what the Fire Festival. It wasn't it like a big flop? Like isn't that the whole?
It was like what Coachella is, and like she wanted to be her, but then instead she just was like, here's a tent.
Oh. Yeah.
There's a documentary about it on Netflix.
Yeah.
It's so good.
It's like the internet like convention where there was like a ball pit or something that was really sad.
Oh, that's like DashCon.
DashCon. Wow.
Yeah, it's
So,
a really cool documentary.
let's go to our last, or no, we have two little topics to talk about. So I'll do a first little. So you've already seen these reactions can do kind of complicated things. And here, if I have these two ketones here, and I add some base, I want you to take 30 seconds, and I want you to try to see which of these do you think would form with an aldol condensation reaction. So just try to like map out a few of them if you see like what would become an enolate, what would it attack, and which product would it form. So how many people think it would form just one of these? Can you show me on your finger how many of these 8 do you think it's going to form? Were you able to find ways to create 1 or 2 of them? Or was that not enough time?
To go over this.
So, which of these do you think is formed, or how many of them? Are there any where someone feels confident, I know this is formed, one of these? Everyone said no. They said, absolutely not, thank you. Well, I'll go ahead and do the reveal then. The plot twist is all of them are formed. So like if you made the red-orange enolate on the outside and attacked this red-orange one again, that would get A. And if you attacked the green-blue one, you would get B. If you made the inside enolate here, that could get C or D if you attack either of these. And then you have the same thing for the enolates on either side of the green-blue one. So, chaos. Chaos. So we need ways to control the chaos. And this is our big idea here. There are some strategies that we can use to limit all of these potential reactions that could happen. And the main strategies are symmetry, using compounds that lack alpha hydrogens, using ring size, and then using sequential addition. These are kind of pretty simple ideas to get, and you guys are not going to really have to supply these very often. It's something that you should see just to kind of show how complicated it could be and how we are presenting ways that there are only 1 or 2 options of doing something. So symmetry. Here, if we made this enolate versus this enolate on the other side, are they different? No, they're the same. So this, you can only form 1 enolate, so that already cuts the possibilities in half. Similarly, if you didn't want to have an option between 2 enolates, you only want 1 option for an enolate, just use something on the other side that doesn't have alpha hydrogens. So like a benzene ring, an OMe, a tert butyl. Here there's just no alpha hydrogen, or there's no alpha carbon, so no alpha hydrogen. And here we have another kind of ring here, no alpha hydrogens. Now, if we wanted a molecule to straight up only be our electrophile, never be our nucleophile, never form an enolate, then put those things that block alpha hydrogens on both sides of the carbonyl. And in situations like this, none of these can be nucleophiles. These can only be electrophiles. That's another way to kind of control the chaos. Similarly, and this is connected to the Rasputin dance problems, in choices where you're doing an intramolecular reaction, choosing whether or not you do the inside alkene or the outside alkene will control the size of the ring that you form. So for example, over here, if you form the enolate over on that side, you'll get an 8-membered ring. And you can count the carbons 1, 2, 3, 4, 5, 6, 7, 8 to attack. Whereas if you do the one on the inside, you'll get a 6-membered ring. Which one do you think is going to be more stable, 8 or 6? You would think. But what's the one that we spend so much time talking about? 6, the cyclohexane. And it's because that chair structure is really especially stable for the Newman projections. They can get this completely staggered conformation. And so even though big rings are not as strained as small rings, they're still not as stable as a 6-membered ring. Our kind of gold standard are 6 and 5-membered rings. Similarly here, if you do on the inside, you'd form a 4-member ring. If you do on the outside, you do a 6-membered ring. And then over here, can we form a enolate on this carbon, or on this carbonyl? We have an OMA and we have 3 carbons next to it. So this side we know is the electrophile. And so then our options are really between, do we do on the outside and make it a 7-membered ring, or inside and do a 5-membered ring? In this case, both of these would be pretty okay. The 5-membered one's a little bit preferred, but again, it's a way that we can kind of control the options because it's going to form the more stable one. The last one is not something we get into much in this class, but is a big part of other classes, where another way that you can control this is, what if you take one of your molecules and turn it 100% into enolate? So you use a really strong base, this is one called LDA, and make only enolate in your beaker. And then the molecule that you want to be the electrophile, you dropwise add in. So what that's doing is when you add in your electrophile dropwise, that electrophile is immediately being attacked by the enolates and doing the reaction that you want. You are not going to have a situation where that enolate is going to be around long enough to be deprotonated and form its own enolate. And so it's a way to kind of control it. But again, it's a little bit beyond what we do. So, methods of controlling the chaos. This brings us to our last topic of the last section. I'll do the sad. Enolates can do other things. They're just a bunch of other enolate reactions that exist, and this is kind of the other category. So, enolates, they could attack an enone. And if they attack an enone, they're going to typically attack at this 1,4 position. I say typically, they're going to always attack at the 1,4 position. And when we do that, this is just the conjugate addition arrows that we saw from lecture 3. So this one really intersects with lecture 3. And we get out this characteristic product here, where we have 1, 2, 3, 4, 5 carbons between 2 of these carbonyls. That has to do with the fact that here we have the 1, 4, and then we're doing an alpha addition. That's where we get the 5 from. But again, this is something that looks really crazy, and so we're going to need a way to spot it. And if we can learn a 1,5 dicarbonyl as something to look out for, that can tell us, we did a 1,4 addition that we call the Michael addition. This is also typically done with a beta dicarbonyl as the starting material. We typically don't do it with a single-sided carbonyl. So another way to spot it. Enolates can do alkylation. They can do a simple SN2. So this kind of intersects with lecture 6. So we actually saw this at the beginning of section today, where we had an enolate do a backside attack into a sigma star carbon bromine, or carbon halide. And the thing that we're looking for here in the product to spot it is we've just added an alkyl group. This one is one of my favorites, a decarboxylation. So the whole concept is, what if we make an ester disappear before your very eyes? We would start off with a dicarbonyl with an ester here, And then, using our lecture 5 reactions, we would turn the ester into a carboxylic acid. So ester into carboxylic acid. This is our lecture 5, ester hydrolysis. And that was just these reagents. So if we had NaOH, that would make our carboxylic acid. But then if we add heat, this interesting thing happens. Where here, we get a transition state in this molecule that's a 6-membered ring. And it's real fierce. Like there's a hydrogen bond that kind of holds it in this position. And what's even more fierce about it, and y'all would never have to draw this in this class, but it's so cool. This 6-membered ring transition state is a chair. Like you would have carbonyl, and then a hydrogen bond, and then the O, and then carbon here, that has a carbonyl, and then this, and then this. Like that's fierce. A 6-membered ring transition state that's a chair. Come on. And so this is a really stable intermediate. And when you add heat, there's enough energy for this interesting kind of cyclic reaction to happen, where it reminds me a little bit of the MCPBA era, so it all goes around in a circle. When we do that, we wind up with CO2, a gas being released. Anytime that we can release a gas, it is super favorable in terms of our like delta G favorability. And then what we get formed on the other side is an enol that then we can tautomerize back to a ketone. Lecture 10. So again, there are all these really nice resonances with the other lectures in the class. And it's really enolates just acting as nucleophiles in the same way we've seen other nucleophiles act. The last kind of reaction here is really a reaction scheme. It's an idea for kind of a synthesis or a big mechanism called the Monic reaction, which I think Tim called the Manic reaction. I know some people do. I think he was German, so it's like Monic, the Monic reaction. I don't know. But the scheme. We have a ketone, an amine, and an aldehyde. And what we do is, using our lecture 5 reaction, we form an aminium, or in slightly acidic conditions, pH around 5. We've formed an aminium. Then our ketone is going to tautomerize into an enol. And we go into an enol because, again, we're in slightly acidic conditions. We are not going to do an enolate. And the big, like, dramatic action movie part is this enol is going to attack the aminium. Just kind of like attacking a carbonyl. The product that we would get from this whole reaction scheme is this beta-aminocarbonyl. So again, we're creating alpha-beta bonds, which should come as no surprise with all our enolate chemistry that we've done today. And then beta, we have this NH2. So you have some straightforward monic reactions in skill builders, but I want to talk about the challenge problem 6, which is monic-like, but is not exactly like it. In the last few minutes, I'll try to keep it short. I'm just going to do this, and then one last kind of final note. Here, do we have a beta-aminocarbonyl in our product, like this? Do we have any carbonyl in our product? No. So how do we know that we're trying to do something monic-like? Well, they write pH around 5. So we should be thinking of amine things. And also we have nitrogens present. So that's kind of the tip-off if we have a monic-like thing. Well, the first thing that we would do in our monic is we would try to make an aminium. So where do we have like an aldehyde and a nitrogen that could potentially make an aminium? Well, we have 2 nitrogens. Do you think it's the top one or the bottom one? The top one. Okay, and this top one, do we think that it's, no, I'm going to say pretty confidently it's probably going to be that nitrogen in the product, right? Because it would be really hard to bust this one out of this big ring thing. Okay. Well, then if this is our aldehyde carbon, would that make sense to be this one? If we like number this around, it would be a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That works. That would form a 5-membered ring. So you're going to have to do the full mechanism on the homework. But we would do our minium formation from lecture 5. And we would get to this structure. And then once we had this aminium, this is the part of the monic reaction, the classic one, where we would have an enol come and attack it. We don't have an enol anywhere, but look at the bond that we need to make. Like, we need to make this bond, right? So if I label that third carbon red, that carbon is here. Is that connected to any functional group that's kind of like an enol? What functional group? Who is she? She's an enamine. Which, remember, enamine is just the nitrogen flavor of an enol. So we can do exactly what a enol would do. We push down, go attack, and then we form our ring this way. And so I think there might be like a final protonation or deprotonation step. That's going to be the big thing for this reaction that's tricky. This one's a skill builder we're not really going to do. It's decarboxylation and alkylation. It's a really great kind of classic problem, so I would definitely suggest spending time with it. This is a very kind of line reaction. You could do this type of transformation really easily, whereas something like a monic typically wouldn't be on like a synthesis. So the big thing I want to leave you with for this lecture is the hard part is seeing this complicated reaction that we're going to put in front of you and figuring out which reaction happened. And so our only tool for figuring out what happened, again, for touching the earth and said, something happened here, is identifying these functional groups, these new kind of big functional groups that we were talking about as the product of these reactions. So I would heavily encourage you to memorize these and make this your kind of solid tool set for starting any kind of lecture 10 reaction. We will do a little bit more lecture 10 stuff in the review lecture on Tuesday, but that brings us to the end of our last section. So I'm just gonna say very briefly, I've really enjoyed working with y'all. Like I love working on S17. I've come back for like 6 years because I enjoy it so much. It's the class where I like realized, oh, I really like teaching. And like, I don't even like organic chemistry that much, but like me being like, I have to make y'all tolerate this made me be like, oh, okay, organic chemistry is the best thing in the world. And so I've been trying to kind of bring some of that energy to it. But it's just been really lovely, like working with y'all in section and help room and getting to know y'all. I'm like proud of all y'all have done. Like imagine what you know now and what you're doing now with organic chemistry compared to truly 6 weeks ago. That's a crazy amount of difference. And so again, I think y'all should be really proud of what y'all are doing. I've really enjoyed this and thank you for your time. Yeah. Yes.